Okay, so these waves are said to be in phase. All right. Now, these waves down here, that's these, notice how one is offset by the other. This one starts, it goes through one complete wavelength, and then this next one starts. Then these are said to be out of phase by one wavelength. So notice that these waves are also in phase. They look the same. Once you get past this point, they look the same. So these are also said to be in phase. So being out of phase by one wavelength is the same as being in phase. We could also say that these waves are 360 degrees out of phase. Those all mean the same thing. Out of phase by one wavelength, out of phase by 360 degrees, or that's also equivalent to being in phase. Now these two waves, notice we go through a cycle of a half a wavelength and then the next wave starts. These are said to be out of phase, I guessed it, by a half a wavelength. Notice that they are also completely out of phase. We would say that these two waves are 180 degrees out, I'm going to abbreviate this, out of phase. Okay, so if they're in phase, we just say they're in phase. But that's also equivalent to being one wavelength out of phase, a shift of one wavelength, but your peaks still line up with the peaks and the troughs still line up with the troughs. All right, so and then that's also equivalent to 360 degrees out of phase. And then here I have some that are 180 degrees out of phase. Now finally, these two wavelengths are out of phase here by a quarter wavelength. So in this point, complete destructive interference does not occur. Complete destructive interference does not occur here, but neither does constructive interference. You get some places that have a higher amplitude, some waves where they join have a higher amplitude, and some have a lower amplitude, but you have neither complete destructive nor constructive interference. Now these waves that are out of phase by a quarter wavelength, we say are 90 degrees out of phase. Right? Half a wavelength is 180 degrees out of phase, quarter wavelength is 90 degrees out of phase, and then a full wavelength is 360 degrees out of phase. Okay, I think we've already said this, but let me just put it in writing. For two waves to be coherent means neither that the waves are in phase nor out of phase. It just means that their phases remain constant with respect to one another. That those two waves do not shift with respect to one another. That if they're a half wavelength out of phase, that they remain a half wavelength out of phase. If they're a quarter wavelength out of phase, they remain a quarter wavelength out of phase, or 90 degrees out of phase. Would be the same way to say that. All right. I have a PhET simulator. You can find that. You can just go to Google and search PhET wave simulator here for wave interference. I already have it running. It's a Java. And this shows two waves. They're being produced. These are electromagnetic waves. I have these two waves that are being produced here. Notice that as they come on, let me turn off one of these. I guess I'll turn this one off. If I turn this one off, notice that this one puts out waves. It has peaks here where it's bright and troughs where it's dark. And then if I turn on the other one, notice that where the peaks come together, I get a really dark spot, and where the bright spots come together, I get an even brighter spot. Now this shows the electric field, or the light, as it may be, where those parts come together. And so, for example, here, I get a really bright spot here, and you can see this shows the magnitude of that wave, and then over here it shows the screen. We'll get into this. This is called double slit diffraction, where we have the interference of these two waves, and where the peaks and the troughs line up, I get destructive interference, and where the peaks and the peaks line up, I get constructive interference. You can do these quick tests now. Have these on your online quiz. And here's another. Here I have two waves that are different. I'll add them up. What is the net that you get? And then here's another wave about destructive or constructive interference, where I had these two waves that are traveling different distances. You'll see these on the online quiz. Right. Most light sources change phase very quickly, so it is very difficult to bring two sources together in a coherent manner. One way to do this, and Thomas Young did this in his double slit diffraction experiment, is that he took a light source over here. Right. Now, a light bulb, the phase of a light bulb is constantly changing. Right. But if I can split that light bulb and make it two separate sources, then I will have two separate sources for which the phase is constantly changing, but both sources will be changing in the same way. Right, so I have a constantly changing phase here. Right, so I can't bring two light bulbs together because they'll constantly be changing phase, and they'll constantly be changing phase differently. Because, you know, a light bulb is just a filament that's really hot, and the phase of the light that's coming off of it is going to be changing a lot. It's not coherent. But in this way, by putting it behind a slit, then that light is emitted from that slit, and then I get two basically replicas of that light bulb, so that the light source in each is changing constantly in the same way. So both of them are the same. And then this gives us a coherent light source. Right, so because the light is coming from the same source, right, it is coherent. I have these two waves that are always constantly in the same phase. Even though that phase is always changing, they're always in the same phase because they originated from the same source. And so that was a clever way in order to produce this coherent light source. Right, we'll pick up next time with Thomas Young's double slit experiment, which will be sort of our second big topic here.